All right, let's dive right in. Welcome to today's explainer. So today we're tackling a topic that honestly so many people overlook, but it is an absolute high-stakes system design imperative: LLM model formats in production. We tend to think of AI as just this magic math, right? But the actual format of that math, that dictates whether your deployment thrives, wastes thousands of dollars in compute, or just outright crashes your servers.
Think about it for a second. What actually happens between I just trained a model and it's actively serving requests? That is the ultimate and frankly often forgotten journey of an LLM. It has to move from being just a dry technical footnote in a data scientist's Jupyter notebook into a robust, scalable piece of software. And exactly how you bridge that gap? Well, that's a matter of critical operational success. So the crucial point here is that the stakes are incredibly high. Making the wrong choice in your model format isn't just a minor, inefficiency. A wrong choice can literally mean a 10x slower load time because your system is bottlenecked by constant memory copying. Or worse, it can introduce a massive security hole directly into your infrastructure. Or it could even result in outright hardware failure, where the model simply refuses to run on the expensive chips you already paid for.
Here's our roadmap for today. First, why model formats matter. Second, training versus safe distribution. Third, hardware, edge, and local. Fourth, the master breakdown. Fifth, designing the architecture. And finally, number 6, operational infrastructure. Let's get to it.
Section 1. Why model formats matter.
When people say the model, what are they actually talking about? Usually, it's just a massive folder of numbers, the weights, plus some crucial metadata like tokenizer rules and layer configurations. But how that folder is packaged dictates everything about its lifecycle. It determines its safety, its loading speed, and its hardware compatibility. Essentially, you're choosing exactly where on the danger to safety paradigm your application is going to live.
Moving right along to Section 2. Training versus safe distribution.
Now, what's really interesting here is the battle between the two foundational formats. First, you have Pickle, or .pt, which is PyTorch's native format. Now, it's great for resuming training because it captures the optimizer state. But, and this is a massive but, the torch.load command can execute arbitrary code. Downloading an untrusted Pickle file is literally like downloading a random .exe file off the internet. It's a genuine security threat. Enter Safe Tensors. Built by Hugging Face to fix this exact vulnerability, Safe Tensors acts as a shareable firewall. It strips out the executable code and that optimizer state, storing only the raw tensors. This allows for zero-copy memory mapping. That means your model loads blazingly fast directly into RAM without executing a single line of risky code.
All right, on to Section 3, hardware, edge, and local.
So, what happens when a model needs to leave those massive cloud GPUs and run out in the real world? Well, to understand local deployment, you first have to understand quantization. This is the process of compressing a model's weights. Think of it like taking high-precision 16-bit numbers and crushing them down to 4-bit. You lose a tiny, tiny bit of accuracy, sure, but you drastically shrink the file size so a massive LLM can actually fit into the limited RAM of everyday consumer hardware. And this is exactly the superpower of GGUF, the GPT-generated unified format. It is absolutely the self-contained king of local inference. GGUF packs the quantized weights, the tokenizer, the metadata, the whole shebang into one single file, perfectly optimized for running offline on a standard laptop CPU.
And this brilliantly builds to two more powerful formats you really need to know. First up is ONNX, the Open Neural Network Exchange. ONNX is completely hardware agnostic. Instead of just storing weights, it stores the full mathematical computation graph. This means the ONNX runtime can read that graph and just automatically select the most optimized backend, whether that's a standard CPU, an NVIDIA CUDA GPU, or a specialized NPU. And it does this without you having to rewrite a single line of code for cross-platform deployments. It's a total game changer. Then there's MLX, Apple's open source framework. This one is Apple's Silicon native. It takes full advantage of the unified memory architecture on M-series chips. Because the CPU, GPU, and neural engine all share the exact same memory pool, you get ultra-efficient, lightning-fast performance on Macs with zero costly memory copies.
Which brings us to Section 4, the master breakdown. Let's build a quick mental map to consolidate all of this so you know exactly which tool to grab for which job. Doing internal research and need to pause and resume training on a controlled PyTorch cluster? Use Pickle. But the minute that model needs to be downloaded, distributed, or served in production, Safe Tensors is your gold standard for security. Now, what if you're building an app that runs locally on a user's device without internet? GGUF is your offline champion. If you're an enterprise deploying across a chaotic mix of cloud GPUs, local CPUs, and dedicated AI accelerators, Onyx gives you that cross-platform flexibility. And finally, if you're building exclusively for the Mac ecosystem to leverage those M-series chips, MLX is your dedicated choice. Now, keeping all of that in mind, there are a few other emerging and adjacent formats you'll definitely encounter out in the wild. I just want to briefly acknowledge them so you aren't surprised. You'll see TensorRT, which is NVIDIA's format for maximum performance GPU inference. There's TensorFlow Lite for mobile and embedded deployments, and Core ML, which is Apple's broader on-device machine learning format outside of the MLX framework. Moving to Section 5, Designing the Architecture. I want to speak directly to the solutions architects for a minute, the folks tasked with safely transitioning these models into production. How does this translate into intentional system design? Architects, remember this. There is no single magical format for production. Multi-target deployments require a rigid pipeline. Step 1. Enforce a strict security boundary at ingestion. Treat any untrusted pickle file like unsigned malware. It simply does not pass. Step 2. Establish a canonical model registry using safe tensors as your undisputed gold standard. Step 3. Build a multi-target conversion pipeline where you automatically produce GGUF or Onyx files specifically tailored for each downstream target environment. And finally, Section 6, Operational Infrastructure. Now, let's pivot to the AI platform engineers. We really need to emphasize the immense weight of operational governance here. Platform engineers, these are your strict operational rules. First, never, ever torch.load an untrusted pickle file in production. Just don't do it. Second, quantization is a trade-off between memory footprint and intelligence, right? So you must track quantization levels per environment as a release variable and benchmark the accuracy loss. Third, monitor your hardware-aware routing. If an ONX model silently falls back to a CPU on a highly expensive GPU node, that is a massive hidden latency bug eating your cloud budget. Fourth, ensure artifact provenance. Every GGUF or ONX file must be a versioned build output traceable to its safe tensor source. Never use hand-converted files. And finally, plan for independent rollouts and rollbacks on edge fleets, since they often lack the connectivity for rapid hotfixes. This all really brings us to the ultimate scalable use case. Your goal as a platform engineer is to build exactly one automated conversion service. This single service takes a registered safe tensors model, produces and benchmarks your GGUF and ONX variants, and only promotes those artifacts that actually pass your stringent quality thresholds into production. I want to wrap up with this incredibly powerful quote from our source material. A model file format looks like a technical footnote, but it quietly decides whether your model is safe to share, how fast it starts up, what hardware it can run on, and whether you can keep training it. Getting this format right at design time transforms deployment across the cloud, edge, and local hardware into a smooth pipeline decision instead of a recurring 2 a.m. fire drill. So I'll leave you with this. When you pull that next open source model off the internet, are you confidently loading a secure firewall of weights, or are you just blindly executing a folder of unknown code and hoping for the best? Dig into your infrastructure, audit your formats, and keep building securely. Thanks for joining me on this explainer, and we'll see you on the next one.